Welcome to my demonstration on basics of data loading and 3D visualization in 3D Slicer. This video is done as an assignment for medical imaging course at IIT Tirupati. This demonstration serves as an introduction to basics of data loading and viewing DICOM images and 3D models in 3D Slicer. DICOM is the standard for the communication and management of medical imaging information and related data. DICOM stands for Digital Imaging and Communications in Medicine. In this tutorial, you will be able to load and visualize diagram images in Slicer. You will be able to perform volume rendering of CT data. You will be able to load and visualize 3D models reconstructed from MRI data. In this tutorial, I used 3D Slicer version 4.11.4 and 3D visualization dataset provided in 3D Slicer website. Let's start the 3D visualization demonstration on 3D Slicer. This 3D Slicer official website. This is the download link. You can find different 3D Slicer versions to download. I've downloaded this version 4.11.4 for this demonstration. I found this material for 3D Slicer 3D visualization demonstration in this link. If you click this Slicer training link, you can find different tutorials, different aspects of 3D Slicer. You can visit any one of them and train yourself. This demonstration is based upon this 3D visualization, data loading and 3D visualization. You can find this data set here. If you click this, you can download this data set. I've already downloaded it. Let's see how DICOM data is loaded onto 3D Slicer. We use thorax abdomen DICOM data for this demonstration provided by the 3D Slicer website. Here is the dataset after unzipping the dataset downloaded from 3D Slicer website. Drag and drop the dataset 1 thorax abdomen folder onto the 3D Slicer. Slicer displays the user interface of DICOM module. The patient 1 study contains a CT thorax abdomen dataset. Select patient 1 and click load. Slicer displays the axial, coronal and sagittal images of the CT thorax abdomen dataset. On the diagram to display the list of modules of Slicer. Select the module volumes. Click on the CT abdomen preset to automatically adjust the window or level display of the CT dataset. See the change in the images. Position the cursor over the red banner in the red viewer to display the slice menu. Click on the links icon to link the slice controls across all slice viewers. Click on the eye icon to display the three anatomical slices in the 3D viewer. If you disable the eye icon for any of the three planes, you cannot view that plane on the 3D slicer. So you have to enable eye icon for all the three slices, that is sagittal, coronal and axial.
Click on the Slicer Layout menu icon, and select the conventional widescreen layout.
Use the right mouse button in the 3D viewer to zoom in and zoom out. Use the left mouse button in the 3D viewer to rotate the images.
Position the mouse cursor over the pin icon in the blue banner of the 3D viewer window to display the 3D view controller. Click on the second icon on the top row of the 3D view controller to center the 3D view on the scene.
Select the volume rendering module in the list of modules.
Part 2. Volume Rendering. Volume rendering techniques enable 3D visualization of 3D datasets. The volume rendering module in Slicer enables interactive 3D visualization of DICOM images. Click on Preset in the Display tab and select the preset CT Cardiac 3. Select VTK GPU Raycasting Rendering. Click on the eye icon in the Volume tab to display the volume rendered image in the 3D viewer. Use the Shift slider to change the transfer function and display the error data. Click on Display ROI to display a region of interest, ROI, in the 3D viewer and check the option Enable. Turn off the visibility of the axial, sagittal, and coronal slices in the 2D viewer. Position the ROI around the left kidney using the color handles. Click on the eye icon to display the volume rendered. Slicer displays the volume rendered image of the left kidney. Extend the ROI to generate a volume rendered image of the right kidney. Click on File and then close Scene in the main menu. Part 3. Loading and viewing 3D models. The directory dataset2_head contains the slicer scene called head_scene.mrb. The scene contains 3D models from the SPL Brain Atlas developed by the Department of Radiology at Brigham and Women's Hospital, Harvard Medical School. Slicer scene. Slicer stores all loaded data in a repository called a scene. Each data set, such as an image volume, surface model, or point set, is represented as a node in a slicer scene. All slicer modules operate on the data stored in a slicer scene. Drag and drop the file head_scene.mrb located in the dataset2_head directory into Slicer. Slicer displays a 3D surface model of the head and 2D MRI slices. Position the cursor over the pin icon to reveal the slice menu and click on the eye icon to display the axial slice in the 3D viewer. Select the Models module in the list of models. Slicer displays the list of 3D models loaded in the scene. Select the model skin.vtk. Lower the opacity of the skin model using the visibility slider. The skull bone and eyeballs models appear through the skin. Select the skull bone model and click on the eye icon to turn off its visibility. The white matter and optic nerve models appear through the skin. Click on the eye icon to display the coronal slice in the 3D viewer. Select the hemispheric white matter model and select the option clipping. Move the coronal slice posteriorly to display the optic chiasm. Slicer displays a 3D view of the optic chiasm. I demonstrated isolation or display of only optic chiasm. We can also isolate or display models of other parts by clipping other parts like white matter, skull, eyeballs, etc. We can also change the color of different components in the models. We can rotate the model or spin it interactively with a human icon indicating the orientation of the model below. In other words, we can view models of different parts interactively in 3D Slicer. It is user-friendly. Conclusion. 3D Slicer provides advanced functionalities for loading and viewing 3D medical imaging data. The tutorial demonstrates how to use volume rendering and 3D surface modeling for interactive visualization of CT and MRI data. For more details, visit these links provided in the description.